Good morning. Okay, so the exam results should be out. So some of you, your TAs might have put them on WebAssign already. If not, they should be doing that soon. The course-wide average is 60, which is pretty good for a second exam. But unfortunately, we don't have the cutoffs yet. I have some numbers in mind, but there are 3 of us teaching the course, and we all have to agree to those numbers. And we're still getting a consensus there. So by no later than Monday, I'll give you the cutoffs, possibly later today by email if we somehow agree upon something. All right? But I can tell you right now, the cutoffs will be more generous than the last exam. That I can say for sure. Somebody's happy? Good. All right, but so sorry about keeping you wait, but I'll try to give those to you as soon as we have those numbers. Today we're going to look at section 16.5. We're going to look at 2 additional vector operations. One of these operations is called the curl, and the other one is called the divergence. Now remember, if you take the gradient of a scalar field, you get the partial derivative of f with respect to x in the I component plus partial f partial y in the j component plus partial f partial z in the k component. Okay, so that we know this already. So we're going to learn a little bit more about this gradient upside down triangle thing. This upside down triangle actually has a name. It's called the del operator. And what it really is, the del operator is a vector-like quantity, but it's not a vector. So it looks like this. I'll write it down first and we'll talk about it a little bit. Okay, so that's what the del operator looks like. It's kind of like a vector because it has I, j, k components, but it doesn't have a magnitude by itself because we know these partial derivative operations mean nothing by themselves. So it's kind of like a vector, has some kind of direction, has some kind of magnitude if it is applied to something. By itself, del is meaningless. Just like this thing by itself means nothing. Only when it is operated upon something, hence the name operator, does it gain a meaning. Okay, so let's revisit this gradient here. Now we know what del really looks like. We can see how this thing came out. This is I times the partial derivative with respect to x operation, partial with respect to y operation, and then k partial with respect to z operation, times this scalar function f. So when you multiply this together, the I component becomes partial f, partial x, right? This guy and this together, now they have a meaning when they are put together, partial f, partial x, and that goes in the I component. Same thing with this, partial y, and f together gains a meaning. It means take the derivative of f with respect to y, and that goes in the j component. And same thing with the last one. So that's where this gradient thing really came from. We had this operator called del operator. It looks like a vector, but it's not truly a vector because by itself, it doesn't have any meaning to it. Okay, now we're going to do more with this del operator now. We're going to define a new operation. We'll call that the curl. Suppose we have a three-dimensional vector field, pi plus qj plus rk. The curl of a vector field is defined as the del operator crossed with the vector field f. Del cross f gives you what's called curl. So when you do the cross product, remember you treat del like a vector. When you cross two vectors, you do the determinant with the second row being the first vector. So del is not a vector, but it's vector-like, right? So we're going to put del in the second row. And del has partial x in the I component, partial derivative with respect to y in the j component, and partial derivative with respect to z in the k component. All right, so this is del. Del is in the second row. And then f goes in the last row. P, q, and r. And we'll, of course, assume that p, q, r are differentiable and continuous and all those nice things. Now you do the cross product as usual. In the end, you will get this thing. It's just the result of a cross product that you already know how to do. All right, so this is what's called a curl of a vector field. Don't bother memorizing the exact expression in the big box at the bottom. Memorize this one here. If you know curl is del cross f, you can always do that on the spot. Note that curl of some vector field is another vector field. Okay? The curl of a scalar field doesn't mean anything. You can't do a cross product with a scalar, right? So there's no such thing as a curl of a scalar field. Curl can only be applied to a vector field, and the end result is another vector field. Okay, so if we cross del with something, we get a curl. The second operation we're going to do is when we dot it with something. The divergence of a vector field, again, let f be PQR, is del dotted with F. And very often you'll see it abbreviated as DIVF. Okay, so if you dot these things together, del, remember, is a vector with these operations that don't mean anything by themselves, but they gain a meaning when they are applied to something. So here's my del, a vector-like quantity that doesn't mean much until it is operated upon something. So we get partial p partial x plus partial q with respect to y plus partial r with respect to z. And the divergence operation produces a scalar field. The dot product of two vectors is always a scalar. Same thing here, the dot product of a vector and a vector-like quantity in the end gives us a scalar. Okay, let's try this on something. xy squared z cubed plus I component plus x cubed y z squared j plus x squared y cubed z k. And let's find the curl and divergence of this thing right here. Curl is del crossed with F. Do our usual cross product determinant. Del is the first vector in quotes, right? So goes into the second row. And then F, whatever F looks like, xy squared z cubed, x cubed yz squared, x squared y cubed z. And now we do our cross product. Let's see, the I component, you cover up the first row and first column, find the determinant of this. So we get 3x squared y squared z minus 2x cubed yz, and this goes in the I component. Minus the j stuff here, we get 2x y cubed z minus 3xy squared z squared k. And remember, in the j, when you do cross product, the sign flips. And finally, the k component, we get 3x squared yz squared minus 2xyz cubed. Oops, that's a j, sorry. K. Okay, so that's what the curl is. Now, what does a curl mean? Well, we'll talk about that in a little bit. The curl in different applications can mean different things. I'll give you some examples a little bit later, but for now, let's just concentrate on the operation side of these things. So that's the curl. It's a vector field just like F. At any point in that space, we can find a vector that represents the curl of that. What that means, again, is application dependent. Divergence is much easier. It's del dotted with F. So this is del ijk component dotted with F, ijk components 2, and let's see, when we dot them, we get y squared z cubed plus x cubed z squared plus x squared y cubed. Okay, once again, it has some kind of physical meaning depending on what you're dealing with. But for now, let's just focus on the operation again. So there you go. These are the two operations that you can do with the del operator. Cross them, you get curl. Add it with something, you get divergence. Now what comes out, you got to remember, curl gives you a vector field, whereas the divergence gives you a scalar field. And they both have to be applied to a vector field to start. There's no such thing as a divergence of a scalar. Because you can't dot a vector with a scalar. Now, interesting about this curl is, if we have a vector field, and we know it is conservative, so that means F is the gradient of some potential function F. Let's see what happens when we do the curl of this thing. In this case, the curl of the vector field big F is equivalent to the curl of the gradient of the potential function. Curl, gradient. So this is sometimes written as curl, grad, little f. And let's see what we get. Let's just carry out the usual cross product. I, J, K. Second row is the del operator. Partial derivative, x, y, z. Last row here is the vector field. We know it's the gradient of a potential function, so let's write down this thing here, fx, fy, and fz. Okay, let's figure out what we get. In the I component here, we're taking the second partial derivative, fzy, minus the second partial derivative, fyz. So that's I component. J component, we get fzx, that's negative, sorry, fzx minus fxz, j, plus k component, fyx minus fxy. So what do we get? We get a zero vector, okay? This is 0I plus 0j. Remember, the curl of something is always a vector, 0k. So this is a zero vector. It's a vector with all zeros. So this means that the curl of the gradient of some scalar function is 0. In words, this says the curl of a conservative vector field is the zero vector. So this makes checking if a field is conservative a pretty straightforward thing. You're given any kind of field, you simply take the curl of it. If it turns out to be 0, then you have a conservative vector field. Now be very careful, the reverse is not true. Just because the curl of some random vector field is 0, it doesn't necessarily mean that it is conservative to begin with. It's like all cats have 4 legs, but not all 4-legged animals are cats kind of thing, right? But this statement is true. Curl of a conservative vector field is 0. So that's a very important result to keep in mind. There's another operation here. Again, we'll let F be PQR as usual. Then from earlier, we found out that a curl is Ry minus Qz, Pz minus Rx, and then Qx minus Py. Okay, so the curl of F, whatever F is, turns out to be that. Let's take the divergence of this thing. Let's take the divergence of this. So this means we're going to do a del dotted with the quantity of del cross F. So this is right here. We're going to take the divergence of this stuff. So that means we're going to get the partial with respect to x of the I component plus the partial with respect to y in the j component, partial with respect to z of the k component, okay, just the standard divergence del dotted with that. So what do we get? We get Ryx minus QZX plus PZY minus RXY plus QXZ minus PYZ. What do we get? 0 again, right? Because QXZ and QZX are the same thing. RXY and RYX are the same thing. And then PZY and PYZ are the same thing. So we get 0 again. So that's another important identity here. The divergence of the curl of whatever vector field, conservative or not, it doesn't matter. Del dotted with del cross with something is always equal to 0. Okay? Curl and divergence are used extensively in applications such as fluid mechanics. That, of course, applies also to air. Aerodynamics is a part of fluid mechanics. In that context, curl measures rotation in the field. Just like the name implies, when you think of curl, you think of things curling around. And that's more or less what's going on here. Curl measures rotation in the field. Think of a whirlpool. If you look in a river, you see a rotation in there. That means that there is a non-zero curl. If curl is equal to 0, the zero vector, then often we say the vector field F is irrotational. There's no rotation. Curl measures rotation. If curl is not a zero vector, then there's some sort of rotation. So what this is saying is that a conservative field is always irrotational, right? Because we know the curl of a conservative vector field is 0. Divergence, like the name implies, measures the tendency for the fluid to diverge from a point. Diverge means move away, so I use move away from a point. In terms of fluid, such as air or water, that means the density of that fluid is changing as you move along in that fluid. So very often, if the divergence is equal to 0, F is often said to be incompressible. Okay, so water is basically incompressible. That's why if you jump from a very high altitude into a pool, it would hurt, right? But air is more compressible than water. So different fluids have different compressibility. So if you were to measure the divergence of those things, air would have a much higher divergence than water, for example. Okay, let's try this example here. A little bit different. Let's look at this vector field that is sketched here. The vector field F is shown in the xy plane and looks the same in all other horizontal planes. So that means this is z equal to 0. At z is equal to 1, it looks exactly the same. At z is equal to 2, it looks exactly the same. At z is equal to any k, everything looks the same. Every layer is the same. Okay? So that means that f is independent of z, and its z component is 0. But notice that we don't have equation for this vector field. But we can answer these questions just based on looking at this and do a little bit of operation based on the definition of those operations. Let's look at A here. Is the divergence positive, negative, or 0? Explain. So first of all, based on the things I have underlined in green, especially the second part here, f is independent of z, and its z component is 0. We know f must look like this, p, q, 0, right? It says that z component is 0. So this vector field must be purely two-dimensional. Let's keep in mind what these things mean graphically. P means the horizontal component. Of a vector. And Q is the vertical component. Now let's take the divergence of that. The divergence of this is del dotted with f. And del is partial xyz in the ijk components. So if you dot with this, you get partial p, partial x, plus partial q with respect to y. All right, so even without knowing what f looks like, we can still do something with this just from the picture alone. Think about what this thing means. This means how the horizontal component is changing as x is increased. In other words, as I move across on this graph towards the higher x on any horizontal line, does the horizontal component get bigger or get smaller? And that's going to tell me the sign of px. So looking at this picture here, would you say that px is positive, negative, or 0? Look at the bottom row here. As I move to the right, does the horizontal component get bigger or smaller? Bigger. So that means this must be positive, right? Right? If I move across any one here, looking at the second level too, the horizontal component is this guy right here, and now this is bigger, slightly bigger, slightly bigger. And that applies to all these levels. Does that make sense? Now, similarly for QY, QY means how the vertical component changes as we move up. So this means the horizontal lengthens as we move right. Now looking at this picture here, would you say QY is positive, negative, or 0? Positive, right. Right, so the first level has no vertical component. As I move up, I have some. As I move up again, it gets bigger and bigger. right? So the vertical component is lengthening as we move up. So here, Qy must be 0. So therefore, the divergence of this vector field, even though we don't know what it looks like, if these two things are positive, this whole thing must be positive. Does that make sense? Yes? Okay, very good. The second question wants us to answer about the curl. Now remember, curl is an indication of rotation. Do you see any rotation in that field? If that's water, will you see a whirlpool anywhere? No, right? There's no rotation. There's no counterclockwise. There's no anything that looks like a hurricane in that vector field. Right? We're looking for a hurricane-like thing. We don't see that. It's just things moving away from a point. So based on visual inspection, no rotation probably means curl is equal to 0. Now we got to be very careful with the visual inspection here, because sometimes we're seeing a very small part of the field. So we can't always be certain that we're capturing the whole picture. But we can still mathematically verify what we think is true. So let's verify that. The curl of F is del crossed with F. Remember, we have a two-dimensional vector field here. The vector is PQ with no Z component. Right? So let's see, the I component is going to give me 0 minus, well, negative QZI. The J component is going to give me positive PZ. And then finally, the K component is going to give me QX minus PY K. Okay, now the first two, remember the statement of the problem. The problem says that F is independent of Z. So that means the partial derivative with respect to Z of anything should be what? Independent means as I move across, I don't see any change. If I don't see any change, the partial derivative is? Come on, you know this. If there's no change, what's the derivative? 0. So if F is independent of Z, that means as you move up and down, there's no change. Therefore, the partial derivative must be 0. So all partials with respect to Z are 0. So that guy is a 0. This guy is a 0. Partial derivative with respect to of Q with respect to X. Q is the horizontal component of the vector field. So Qx means how the, what did I just write here? How the horizontal component changes as we move right. Okay? How Q is changing with respect to X. How the horizontal component changing as we move to the right. Looking at the picture here, what do you think that will be? Pick the first layer. What's the horizontal component? Wait a minute. I had it right the first time. Q is the vertical, right? Yes. Okay. No wonder you look so confused. My bad. Let me ask that question again. Looking at the first layer of that vector field, the bottom one, as we move to the right, how is the vertical component changing? It's not changing. It's 0 to start and 0 all the time, right? So what would you say Qx is equal to? 0. What about Py? Py means how the horizontal component is changing as we move up, right? So pick the first column of that vector field. All of them have the same horizontal components. So what we found out from looking at the picture here, all of these are 0, 0, 0, 0. So this turns out to be a 0. So that agrees with our initial visual inspection. We're looking for some kind of rotation. We don't see that rotation. We see a moving away from a point, but we don't see a rotation. So we guessed that it would be a 0 curl, and it turns out to be what we expect it to be. Questions? Okay. Finally, we're going to make a connection of Green's theorem to what we just saw with curl. So we're going to look at the vector form of Green's theorem. Recall Green's theorem says that if you go around a closed loop, so that little circle here means closed loop, of f dot dr, this turns out to be p dx plus q dy, which by Green's theorem means that we actually do a double integral over the region D of partial q with respect to x minus partial of p with respect to y, dA. Okay, remember the picture here. This is our picture here. C is going counterclockwise in a positive orientation, once around in a closed loop. And the region it encloses, that's D. So Green's theorem says that this is equivalent to that. A line integral can be connected to, made equivalent to a double integral over the region. Now let's find out where this thing came from. Okay, remember back then I said the proof of Green's theorem is kind of complicated. But now we can actually see Green's theorem as a consequence of a curl. So we can kind of answer the question why that's the case. Let's assume that we have a vector field. some general vector field PQR, three-dimensional stuff. The curl that we saw earlier is Ry minus QZ PZ minus Rx and then Qx minus Py. Right? Now look at the last component here. This is precisely the same thing that we integrate using Green's theorem. So this is the K component of that. So this means that the Green's theorems, the form of Green's theorem that we saw earlier, is really the double integral over the same region of the curl of the gradient of the vector field, but only in the K component. In other words, we take the curl of whatever we get. And if you only want the K component, you just dot it with a K vector, right? If you dot it with 0, 0, 1, then the first two will go away, and the only thing you get left is the last component. So you take curl, which is this expression, dot it with A, K, and that gives you what we integrated over. So this is why if we apply Green's theorem in a conservative vector field, we knew this was going to be a zero thing. And it's zero because the curl is a zero for a conservative vector field. So the form that we saw earlier came from a more general expression, which is curl of f dotted with k. And this, remember, was also how we used to check for the conservativeness of a gradient of a vector field. If Qs is equal to Py, then we knew it was conservative. But more generally, if the curl, this is a consequence of the curl being zero for a conservative vector field. Okay, I can tell by your faces we've had enough today. And we've had enough this week, I think. So let's end it here. Have a good weekend. See you Monday. you.